Let me just make my final checkings. So we have 57 students in today's lecture, which is a number a little lower than usually. Well, I hope, well, the good news is that I can see that the number is growing. So we have more students. That's good because, um, oh, so you said that I have not uploaded to previous lecture material in Moodle. And you also, there is a complaint that my sounds, that I'm sounding a little bit of weird. Okay, it should be okay. I think that at least I have made no changes in my settings. Okay, so others, you hear me fine. Great. So this is where the cut will go. I mean that I'm gonna edit the beginning of the streaming off from the material that eventually will appear in YouTube channel. So what happens today is that we're gonna extend the concept of generalized forces to inertial forces. And as I mentioned you last Monday, this is gonna be a true horror story. And it is true horror story because this is gonna be computation, I mean, mathematically so involving that I don't think that you ever seen in your life anything like this. So no comparison whatsoever. Okay, so what I'm planning to do or how I'm planning to handle this is that first of all, we're going to take a look at this concept of generalized inertia, it's generalized external applied forces a little more in the details. And I would like you to have a good physical interpretation of what is that they are standing for and what is that they meaning in real life. And then once that is all clear, then we're gonna redo the concept of virtual work, virtual displacement, well, all this complicated stuff, but this time in the case of inertial forces. And at that time, I'm gonna put my highest possible speed, and I'm gonna go over the mathematics by not looking too much about the details, because the details are super, super scary. So you just, breathe deeply, try to relax, and we walk together with this very involving mathematics. And once we're done with that, then again there is the sun shining. That's going to be all pleasant, and then that's when the downhill started. So this is going to be the peak of the mountain. That really is a peak of the mountains, and everything after that will be so smooth, super pleasant, no difficulties whatsoever. But we still have this mountain that we have to climb together. Okay. Now, what follows after this concept of generalized inertial forces is that we're going to look at the details related to this generalized inertial forces, and that brings us the concept of mass matrix and something that is called quadratic velocity vector. Quadratic velocity vector is a little bit of special case, and we will leave that with a little attention. Okay, so with that, let's get started for today's lecture, but I would like to get started by introducing you a few practical matters. First one is again, MEVA seminar. Very highly recommended to participate because this is a good stuff. This is something that you can learn a lot. And not just about the simulation, but the bigger picture about the digitalization and how is European leading companies taking the digitalizations and what are the really the high-end things that they're doing in Germany. I think these companies are mainly from Germany. And also the national, I mean, the leading companies in Finland, how is it they are handling the digitalization and most advanced simulation, and what is the bigger picture than just the simulation models. And I think it is important you to learn that. And that's why I highly recommend you to participate. How you can make it happen is that you need to click this link here, which is a registration link, and you need to do that prior to meeting because then the link for the participants will be emailed, and if you don't have a link, you have no chances to participate. So please do it. There will be no expenses, just a lot of happiness, a lot of good stuff. So please consider to do so. This is a screenshots from the agenda. So it shows a little bit about what are the presentations, and this is a kind of small font, but there are some presentation from Leaper, something from Sandvik, something from Siemens. it makes sense to check those out. And then look at this. Then really good stuff comes next. This is an afternoon agenda, and there's even a presentation that is delivered by me. So please consider to participate. All right. So another practical matter is that Jedi and Mech students, there was a mention that there is an intensive week organized in middle of August, middle of next month. That's not going to take place. So it's not going to happen. And it's not going to happen because all the material that you need in order to do this simulation work will be provided in those online tutorials. So there is no need to travel all the way to Lappeenranta to do the whole things in computer classes. But instead, you can do everything using your home office, your personal computer. So this is not going to be organized. If you have a difficulties with the computer, then that may be the only reason that you are traveling all the way to Lappeenranta to do these assignments in a computer class. But I'm sure that's not your case. I'm sure you have a computer some kind that you can install the MATLAB and Simscape, so it should be the case such that you don't need to come to physically to Lappeenranta. So we are not organizing it, but everything will be provided using these online tutorials. And as you have probably noticed, Suraj has really good instructions that are also available in his YouTube channel. So that will be really the way to learn to use these softwares that are needed to do your simulation assignment. So with that, finally, we are ready to move on to summary of the previous lecture. So the last week, we looked at how to conduct a kinematic analysis. And the first super important piece of information that you need to know about the kinematic analysis is that it is a motion analysis. So it's nothing to do with the forces. I mean, that's incorrect statement because as a post-processing technique, you can also get an estimation about the forces. But the kinematic analysis on its pure form is all about the motion and all about the motion limitations. So what are those? Those are the constraint equations. Constraint equations that are a function of generalized coordinates and possibly time. That is the only information we need in order to carry out the kinematic analysis. And it is used to see, how is the work area of a manipulator. Remember, it was used in this bicycle case to see how are the full state of the bicycle. So that's what the kinematic analysis is about. Okay. So kinematic analysis is okay, so there was a question. I'm sorry that I missed it. My windows are not located in an optimal way. So, okay. Okay, so if not able to participate in the MEVA seminar, am I able to put the material to YouTube channel? I'm not sure. I think the copyright is in MEVA, but I need to ask. But anyways, it may be the case that, the MEVA is offering these lectures later in their website. I am not sure about that, but I will let you know. Okay, I was in kinematic analysis, and I would say that the kinematic analysis can be conducted once you know the constraint equation. So this is only you need. First step, we have kind of like 3 steps to take in kinematic analysis, and those are position level analysis, velocity level analysis, and acceleration level analysis. So it's Q, Q dot, Q dot dot. So we need to know the generalized coordinates in the position, velocity, and acceleration level. And that's, by the way, another very important lesson. So in a kinematic analysis, we travel in this direction, from position to acceleration. In dynamics, we're doing other way around. So we are traveling from accelerations to positions, because equation of motion will be expressed in terms of acceleration. Remember this Newton's second law, which can be written like the external applied force is equal then inertial forces. So these are external applied forces. These are inertial forces. This one here is my q dot dot, if simplifying the case. How this will be solved? It will be solved such the way that the mass will be put it in another side of the equation, and then we have an expression for acceleration. And then using the numerical time integration scheme, we're going to call from acceleration to velocity, and velocity to position. So it's meaning that we're traveling this direction. In kinematics, we're traveling this direction. Okay, so the first one is this position level analysis, which is the most complicated one, because solution for our problem is hidden inside of the equation. So it's not explicitly mentioned, but it is hidden to solution. And that's why we have to use this iterative process to solve it. And the iterative process goes such the way that we're using the method called Newton-Raphson. And in Newton-Raphson, we're solving this Newton difference. Sorry that it becomes to be a little bit of mess. Newton difference is not a solution, but it's telling us what is the way we can update our generalized coordinates to get the solution. And that's where it is iterative nature. Okay, so once you have the generalized coordinates from this procedure, then the next step is velocity. Velocity is simple because you take this equation here, you differentiate this equation with respect to time, you get this one. And now you can simply solve this one because the solution is clearly explicitly mentioned. So it's very simple. So you can just solve this, and you can solve it by having the Tracopia matrix, inverted it, and then multiply that by minus of the constraint equations. Final step is an acceleration, which is complicated, and that's simply because this equation needs to be differentiated one more time with respect to time. And that's going to give us a very bad looking equation. And I'm checking that I got a little bit of information that the connection is not the strongest possible at the moment. Okay, so let me see, maybe I need to relook. I have full battery so I can take these to better position. So hold on, just a second. Okay. Yeah, that's a little bit of problem here in the basement office that sometimes the internet connection is not very strong. I see that I got an arrow. Let me see. It still says that I'm online. Okay, we'll see if it's getting any better. How come it is that low quality? Still, it looks that I'm still online. Are you guys still there? Oh, it works perfectly. Kind of weird because I got the information in my screen that there's an arrow, so there's no streaming any longer, but it seems that it's okay. Okay, so I was here wrapping up the kinematic analysis, so let's move on from the kinematics. Still, I have this arrow in my screen, so it says that it's a big yellow text that would say that no good connection. Okay, so here is more details about the position level analysis, and this is how you see that, the iterative nature. So you need to go around the loop until you get the solution, until this kind of direction where the travel is small enough, meaning that you reach the destination, and that's how it goes. Okay, so if you want to see the details, you can take a look at the MATLAB code that is available in a model site. Now, one critical information or one critical component that is needed in all steps of kinematic analysis is the Tracopia matrix. Tracopia matrix is something that you must understand what it's standing for. So it's a matrix that you can get by using a huge number partial operation, meaning that you have a partial differentiation of all the constraints with respect to all the generalized coordinates. And the dimension of the Tracopia matrix immediately tells you what is a number of degrees of freedom. And remember, the Tracopia matrix must be inverted like it is shown here. So I have here this inverse sign here. So the only way you are able to do that is that the Tracopia matrix must be skew, meaning that they have to be the same number of rows and columns. Number of rows will be equal than the number of constraint equations. Number of columns will be equal than the number of generalized coordinates. Remember that number of degrees of freedom is computed by using this equation. Number of degrees of freedom is generalized coordinates minus constraint equations. These have to be equal to 0 in order to conduct the kinematic analysis. I will ask that for 100% certainty, I will ask that in a midterm exam. So prepare yourself to that. And now, still a little bit of stuff to summarize. And I would like to spend here a little bit of time because this is a kind of like an essence what we're going to do the next. And what we're going to do the next is that we're going to compute the generalized inertia forces. But prior to that, we have to look how are the generalized external applied forces. Again, let me tell you what is that we are trying to do here. We wanted to express the force that is initially expressed by using global coordinates. So it's force vector that is expressed in terms of global x and global y. Okay, so this vector here is sorry about my handwriting, is a vector that consists of two components. So it's a projection along the global x and a projection around with respect to global y. So it's two components. Two components. Two is really the key to understand. So two components. Now, in a kinematic, we're using in a multi-body system dynamics, we're using this equation over and over again to express how is a system configuration and how are the constraints located and so on and so forth. Variables here are Rx, Ry, and angle theta for a one body. If you have two bodies, you're going to have 6 variables. And these variables are called as a generalized coordinates. Now remember what we did in the kinematics. We solved this vector of generalized coordinates in a position, velocity, and acceleration level. Now in dynamics, we have to do that, but other way around. Acceleration, velocity, position, meaning that I have to be able to express my equation of motion in terms of generalized coordinates. Okay, so what that means? It means that everything must be consistently expressed by using generalized coordinates, including forces. And here's what I need to do. Look, I have here global coordinates, 2 components. And I should be able to express the forces by using 3 components, generalized coordinates. And how is that I can do this mapping? How can I convert my force from one coordinate system to another coordinate system? Well, that I can make it happen with help of the concept of virtual work and virtual displacement more specifically. So that's expressed here. And it's a mess. But don't get this mess to be you confused. Because what I want to do is that I want to use this concept of virtual work here, where I have the virtual displacement. And remember, the virtual displacement is something that the time is assumed to be not running. It's like a mathematical tool to introduce this mapping between the 2 coordinate systems. Now, the important thing is that this delta R can be expressed in terms of delta Q. These are my generalized coordinates. The one that makes this relation to be possible is a partial R, partial Q. And this is my miracle matrix that I'm calling as a miracle matrix because it's mapping my force from global coordinates to be in generalized coordinates. How is this mapping? Miracle mapping matrix, how it looks in details, it is expressed here. But this is what we're going to practice next. So you don't need to memorize it. And don't please put any effort to memorize it, but more importantly, try to understand the concept, what it means. Now, once we do this whole thing, here to here and here to here, then finally, we will have this mapping matrix. Excuse me, it's a little bit unclear way that I'm expressing this. This mapping matrix that is then multiplied by forces. And when doing that, then I will have three force component. The forces that is associated to Rx, Ry, and angle theta. That's it. Mapping matrix is very, very important. And it is helping you to express the forces in terms of generalized coordinates. Generalized coordinates. That is a key to answer correctly to my first in-class quiz. And let me take a look. Where is my mouse traveling? Here. Now, let's take a look. How is my first in-class quiz? I can see that I have 81 students in my first in-class quiz. By the way, this is a hint for you. So I always put in my first in-class quiz ready when I'm starting my lecture. So you can go and take a look. How is a question? And it helps you to answer that correctly, because I'm usually explaining the correct solution in my explanation, which is, I understand, lengthy, but still. Okay, here's my question. Physical interpretation of matrix, partial R, partial Q, miracle mapping matrix, miracle mapping matrix. Remember, I asked this last week as well, but the different way, because the last week the options were not the same that I'm offering today. So what are the offers, or what are the options today? Okay, so the first option is that it converts forces to be expressed in terms of constraints. So it's, I'm trying to, explaining it. So it's a relation between the force and constraint. Okay, that's an option. I'm not saying that is correct, but that's just an option. Converts forces to be expressed in terms of body mass. So F mass, is that relation that is offers, converts forces to be expressed in terms of tenorized coordinates. Okay, that is this option. And then makes it possible to describe particle rotation. I don't know how to describe that option, but it's an option as well. And I get the information that still there's a problems to lock into Socrates. Okay. So if you have a difficulties locking to Socrates, please email me again. So I will take a look. What is the problem there? Now I see that I have 60. Okay, so it seems that now there is more problems than usually, and the advice is to use a different browser. That maybe is the way to solve it. Okay, so I'm gonna leave you. No, I'm not gonna leave you, because I can see that maybe out of the 87 students, 73 already entered the answer. So now it's 13 students are thinking. Oh, by the way, another important piece of, so there is a came on already. So we'll see. Okay, would you like to learn what is my guess? Not the guess, but my contribution to lottery. My contribution to lottery is 65, 65%. Okay, we'll see who is a winner. I kind of like, I have to say that I like those of you that are voting 90% or more, but, also it's good to be realistic here. So we'll see. Oh, I see that there are 3 students are still thinking, rest is already done with this. So 2 students are thinking, so I think we are able to take a look. Okay, now there's a lot of guesses, a lot of guesses. So here is, and one is still thinking. So in 5, 4, yeah, we have. So that's it. Okay, so mine was 60. Was it 65? I think it was 65. Oh, look at this! Oh my God! Now I got so confused because the number is really high. So I was really wrong about this. So what is it then? number is, oh my God, 97. 97. I don't think that no one more than 97. I don't think so. No, I don't see the 97 here. So, ooh, that's like hard to believe. Hard to believe. And really good news. Not just that the high percentage, but there is even more than that. No one voted option number D, because option number D, okay, we have a miracle matrix, but even miracle matrix cannot describe the rotation of particle because it is a non-existing thing. So it's not there, not in this planet, not in this planet. Okay, so with that, so we're gonna move on and we're gonna look at a little bit about interpretation of this matrix. I mean, matrix and these generalized external applied forces. So now let's take a look at this example. This is a very, very important example, and we need to spend a little bit of time to look at this because I want you to really to understand what these three components, what these that they're standing for. Okay, so let's get started from the problem definition. So I have here, and again, I need to relook at my windows a little bit to see your comment because this is a kind of nice way to communicate, and I can see that some of them are still thinking that the particle rotation yeah, is the way to go, and it's not the way to go. I am providing that often and never ever vote that. Okay, so I was here, so I'm here. So I have this beam-like body, and in the one end of the beam-like body, I have body reference coordinate system. Sorry that my handwriting today is more messy than usually. Okay, so body reference coordinate system is here. And I have gravity force that is applying in the system. I know the gravity is applying in the center of the mass. Center of the mass, it is assumed to be here in the middle of the beam-like body. And gravity is such that I have here y component of the gravity force is equal to zero. X component of the gravity force is assumed to be zero, and y component is assumed to be minus mass multiplied by gravity constant. Okay. So I know that we have looked this, before, and you kind of have an idea how it goes, but it's still important to do it in order to be able to express what this all means for us. So I wanted to express that force, this one single force that is applying in the system in terms of generalized coordinates. So how can I make it happen? Well, easily. I will take my miracle mapping matrix here, and I will take my force, which this time is a gravity force. I'll have this mapping and force. And once I do the mathematics, I take the first row here, I multiply it by force, that first row by the force, that's going to give me 0. Second one, going to give me minus mass multiplied by gravity constant. And the last one going to give me the mass multiplied by gravity constant L divided by 2 cosine theta. Okay, so this is where we need to start. So I have, first of all, the important thing to realize that I have three components. There will be in-class quiz momentarily where I'm asking how the forces in this simple system, how they supposed to be. And you have to select the option where there are three components because three generalized coordinates. Remember, everybody needs three generalized coordinates. So everybody three generalized coordinates, meaning that the force is 2, they must have a 3 components. All right, so first, I think that I need to go back to this figure to be able to express it. So what this means, these force components. So it means, first of all, that my kind of moving my force here to apply in the origin of the body reference coordinate system. And because I'm doing that, I'm going to introduce also the moment, and the moment will be the force here multiplied by level arm. And the level arm is, of course, this one here. I'm making a little bit incorrect drawings here. So let me take this off to make it, yep. No, I think it is getting one more time. Okay, I think okay. So here is my force applying in the center, in the origin of the body reference coordinate system, and then I have this moment. And the moment is the one that is forcing this body reference coordinate system to rotate. That's going to be my third component. So let's go back here. Okay, these are the components that are applying in the body origin of the body reference coordinate system, and this is my moment component, which is applying in the generalized coordinates theta. So it all makes sense. Look at this. This is not the constant component because, of course, the level arm becomes smaller and bigger depending how is the configuration of this beam-like body. So if it is like this, level arm will be 0. So there is no moment component here. If it is all the way here, it is as large as it can be, meaning that it's going to be L divided by 2. So that is something that is very, very important to you to understand. So those are the components that are affecting to my coordinates Rx, Ry, and angle theta. This is a translational force, this is a translational force, and this is a moment. This moment may be 0 as well. Okay, what is the case that this moment is 0? Well, of course, if this moment of this level arm is equal to 0. One particular case when it is always equal to 0 is that when the body reference coordinate system is located in the center of the mass. And now I'm speaking about the gravity forces only. In this case, there is no level arm because the force is always traveling through the origin of the body reference coordinate system. So in that case, generalized forces will be very simple vectors. So it's going to be like this. So this is the force applying in origin of the body reference coordinate system at the moment 0 because the level arm is 0. Okay, so with that, so I guess that it's getting to be okay. So it's kind of understandable. But here's my in-class quiz for you. Next, okay. So next I'm asking pretty much what I just explained. What is correct gravity? Correct generalized externally applied force is a vector of generalized externally applied forces. The choices are 3 components that are 0 mass minus mass multiplied by gravity constant 0, then 0. Well, you can read this by yourself. This is a mass multiplied by gravity constant, and then this is my last component, which is a moment arm. And these are the components. This is one option, and this is final option. I have no comments on those 2 options. So the game is on. What do you think? How is going to be the success rate in this case? Let me see. How is my streaming? It seems to be okay. No. I think it's good to have this can-do attitude, but if it would be 100%, okay, let's make this game on. So if it would be 100%, what is the way that we will celebrate that? Okay, of course we're going to celebrate that in a way that everyone that entered that answer correctly will get. Let me think. 1 extra point, 2 extra points. Let's put it 2 extra points. That's my best offer. So we'll see how it's going to be. 2 extra points. So a little bit of pressure to you. Okay. Yeah, it would be nice to say that, okay, this course is done, so you can all score 5 out of 5 from this course. I would be happy to do that as well, but we'll see. Okay, so I see that there is a lot of voting for 100%. I don't think that's going to be the case, but it may be high. Maybe high. How high? We're going to learn that soon. And now I will leave you. I see all these votings, and I'm going to move on to next case. My next case is this. This is a very artificial, I have to admit that. But again, I would like to just go through this procedure one more time so you can kind of get the concept of what is the deal with this generalized externally applied forces. So here I have triangular shaped body. So this is a plate, and the plate is connected to ground by a revolute joint that is located here. Now the body reference coordinate system is located in a revolute joint. And then I have two forces that are having the components in global coordinate axis. So it's meaning that these forces will always pointing out this direction no matter how is a rotation of this triangular shaped body. So if the triangular shaped body would be having this kind of configuration, these forces would still pushing this direction, okay? Because the components are not the function of anything. They are just expressed by using global x and y coordinate axis, nothing else. And by the way, in my getting up, because I'm starting to think that what if it could be 100% too? That's possible. It is possible. I see that I have 90 students today and 79 voted, not voted, but entered the answer. So 11 are still thinking. So let's get back to the results in a second. Let me still keep on explaining the problem here. So two forces, one that is located in a point A, the second one that is located in a point B. U-bar vector defining these points A and B are provided in a task. So this is it. How is that we can solve this? And again, I want to compute the vector of generalized forces, external outlier forces. There is no other forces here. So I'm still looking at how is a in-class quiz doing. So I see that 8 students are still thinking what is a correct answer. So momentarily we will go back to that. So now I'm going to do this in an old-fashioned, a little bit of hard way. So I'm going to express the point where the force is applied by using this equation that I'm very much familiar with. Then I'm going to differentiate that particular position equation with respect to my generalized coordinates. And that's going to be my mapping matrix. And then I'm simply able to do the conversion from global to generalized coordinates. Okay, so let's get started. So let's define the point, this point where the force is applied. All right, so I'm going to take position of the body reference coordinate system, and then I'm going to compute the orientation of body reference coordinate system, and then vector u-bar. Vector u-bar is provided here, so this is a matter of substitution, nothing else. And once I do this math, so once I compute this row with this vector, I'm going to get this equation here. When I take this row with this vector, I'll get this equation here. Next, I take this equation, these two components, and I'm going to differentiate these components with respect to Rx, Ry, and angle theta. Okay, so here is my first differentiation, so it's going to give me 1. Ry is not mentioned here, so that's 0. And with respect to angle theta, it's just going to be minus sine theta minus 2 cosine theta. And then I redo it by using this equation, and it gives me second row, 0, 1, cosine theta minus 2 sine theta. That's my mapping matrix. Then I will take this mapping and corresponding force. We'll do the operation, check this out. So there's a transpose operation here. So this multiplied by this going to give me 10. This multiplied by this will give me 10. And then where I am, this multiplied by this will give me this monster equation, which can be simplified as it is shown here. Now I see that 4 students are still thinking in my in-class quiz. So the last ones, soon I will go back to my soccer team. So please enter your answer. Now I will redo the whole procedure for the second force. This is my second force, which is located in that point B. Great. So I'm going to simply take my, where the body reference coordinate system is located with respect to global coordinate system, then orientation of body reference coordinate system, and substituting the information about the vector u bar here. That gives me a vector of 2 components, and these 2 components will be differentiated with respect to generalized coordinates again. So I'm redoing the whole procedure. That's going to keep me, or will keep me, this magical mapping matrix. And now I'm going to take this magical mapping matrix and multiply that with my forces. This is my first component, 10, second, 10 again, and then my monster trigonometric expression, which I'm simplifying like this. My final solution, I simply combining these forces to be in a one vector, and the length of the vector will be 3 components because I have here one body only. So this is my first force expressed in terms of generalized forces, second force expressed in terms of generalized coordinates, and here's my final solution. That's how it is. Now, moment of truth. There is I see that my presentation has actually moved a little bit. I don't know why it is doing that. Hopefully it goes back to, yeah, now this is back in the right location. Okay, so I'm gonna take a look at the in-class quizzes, and then I will explain again what is this partial operation, because this is important, you know, and again, let me repeat it. I'm here to help you to understand. And it really is a great thing. And I really appreciate this, that you using this chat window to asking me to repeat something. This is really, really nice. Yep, I appreciate that big time. Okay, but here, I'm back here. All right, so one student is not sure what is the correct answer. We are not going to wait that, but we're going to take a look how is success rate. And the success rate is, okay, not so great. Not so great. Okay, so last time was a very pleasant surprise. This is unpleasant surprise because I was thinking that the number is higher than 60%. But even some of you were voting 100%. I was thinking in my head that it's something like, I don't know, 95% or something like that. Then it's 60%. 60% is quite low in my mind. So let's look at things again. So and then I will take a look at what are the other commons you have. Okay, so let's go first to this in-class quiz. So let's figure it out. What is a correct solution? Now, this is my in-class quiz. I have here my beam-like body, and the body reference coordinate system is located in the center of the mass. And the only force that is applying here is my gravity force. So first of all, correct solution have to have 3 components because the force have to be expressed in terms of generalized coordinates, Rx, Ry, and angle theta. That's why these 2 choices are incorrect because they don't have enough components. That's why they are incorrect. What is left is option number, first and second option. Okay, now how can I know what is right answer from these 2 ones, out of the 2 ones? Well, the key to answer that is that, here now the force is applying in the origin of the body reference coordinate system. And the third component is always looking how is a level arm with respect to force and body reference coordinate system. Is always looking this distance. And if this distance is 0, that will be multiplied by the force, meaning that the moment will be 0. And that means that this is the only correct answer. This cannot be the correct one because, here, this is non-zero component. Okay, hopefully that's clear. TQ, so okay, so could you also show the TQ question? Okay, yeah, I think is this now clear? I think it is clear. So let's go back to this partial differentiation. Okay, I intentionally not to mention your names because this end up to be in a YouTube and maybe this is against the law. And so I'm sorry, it is against the law to say your name. So I'm not saying, yep, okay, great. So it's good. So then back here, this parcel operation. Okay, so let's look at this. It doesn't matter if we're going to look at the A or B. B is not as messy as A, so let's look at this one. Again, this whole idea how force can be converted from global coordinates to generalized coordinates was based on this virtual displacement. And the virtual displacement is something that allows us to see the relation between the global coordinates. Remember, this is expressed in global coordinates and generalized coordinates. So this is the relation that I'm after, delta R, delta Q. What is creating this relation is this parcel R, parcel Q, which is my numerical mapping matrix. That's what it is. Now, this one here, again, let me emphasize, is a position, which is a vector of two components, differentiated with respect to generalized coordinates. Now, because I'm dealing with the one body only, this is going to be vector of three components. So my two equations that I need to differentiate is this one here, number one, this one here, number two, with respect to Rx, Ry, and angle theta. So the first differentiation is this one here. I got it by using first component of R with respect to Rx. Gonna give me one because this component here only. Second one is again the first component of R with respect to Ry. This was X, this is Y. There is no Y in this equation, that's why this is 0. Then the last one is first component of R with respect to theta. Here is theta located, so this is how I get these components. And then you redo the whole thing, but this time you take this row here and you differentiate that row again with respect to your generalized coordinates. Okay, so clear? No comments. Okay, this is just a moment. This is not going to be a very important thing because the moment is going to be very simple. Okay, so it's key. Moment is very easy to deal with because the moment you can move whatever you want. So this is not going to be a big deal. So if you have a case where again the body is here, your body reference coordinate system is here, and then there is a point force applying here. So you kind of need to move the point force to be applied in origin or the body reference coordinate system. So we'll introduce this moment, which is the force multiplied by level arm. And then if you have additional moment, I think that I need to use another color to make this more clear to you. Okay, so hopefully this. So if I have another moment, so let's say that it's applying in the same direction, you can simply add that to your third component, the one that is associated to angle theta. Very straightforward. That's simple. This is more complicated. This point force moment is very straightforward. You just added that to your third component, and that's it. Now I see that I have spent, it's kind of time for a break, but I don't think that I will have a break because you guys are busy. I'm not so busy, but maybe because you are busy, and maybe it's just better to move on and look at the next topic, which is this absolutely the most painful thing you have ever seen in your life. And that is called generalized inertia forces. So go ahead and take a cup of coffee, drink something, breathe very deeply, a few times, even maybe more than that, because this is going to be a rocky road. And it will be a rocky road because, how we're going to express inertia forces will be kind of like this. So I have mass multiplied by acceleration. And remember from the lecture, I think it was second lecture, we look how is an acceleration. And this was very, very difficult, very complicated expression. And this is where we're starting. This is the inertial force is expressed in global coordinates. That's not good. That's not going to do the work for us because we have to be able to express this guy in terms of generalized coordinates. And how we're going to make that happen? Again, we're going to take this mapping matrix, numerical mapping matrix, parcel R, parcel Q, and that will make this happen. But it's going to be very, very complicated. So there was a question if we should have a break. We definitely should have a break. But still thinking because yeah, this actually this there's a comment in a chat window which says that this deserves a beer, not beer, but heavy liquor, strong alcohol. It needs to be something harder than beer, strong alcohol. Okay, now so I'm still gonna go to this topic. I know that they maybe you're tired, but before you're getting more tired, I wanna go this over and it's like going to dentist. So you feel the pain, and once you go off from the dentist, you feel good. The same hopefully will happen to you. So let's get into dentist. Okay. So first thing, let's look how is inertia forces in terms of global coordinates. All right. So this is exactly what I wrote in the previous slide. Sorry about my handwriting. So it's mass multiplied by acceleration. So this is a r dot dot. But let's make it even a bit more complicated because we are so good in the mathematics and we want to show off like how good we are. So that's why we don't want to express the mass as a mass, but volume integral through the particles within the boundaries of the body. Well, this is of course the same thing. Of course, mass is equal than volume integral over the boundaries of the body. And I mean, over the density of the body, and you're gonna go over these boundaries of the body. So that's what it is. But we want to use this kind of more sophisticated way because we're dealing with these particles, and this is this defining the density of a single particle. So now we're gonna take all these super high number of particles into account by using this integration. That's how it goes. So that's kind of telling what is the role of these particles. They really don't have any roles because they will go in this big mess. So that's this volume integral. Okay, so what happens then? We're gonna take and again, very, very important to understand that this force here consists of two components because acceleration here is expressed in terms of global coordinates. So it consists of two components, which are the acceleration with respect to global x and global y-axis. So this force as expressed here is no good for us. So we have to be able to express that by using generalized coordinates. So now you know the mission. So you know that we are here to express this force in terms of generalized coordinates. And the rest is mathematics, but not this time simple mathematics, but very heavy involving mathematics. Okay, so let's take a look how is a virtual work done by inertial forces. And that, by the way, was this great deal about the D'Alembert's principle. So the D'Alembert's principle, like I made a joke last time that the D'Alembert looked this Newton's second law and he was able to write it like this. And he became super famous. That's not the case. But the case is that inertial forces can be treated exactly the same way than externally applied forces. Exactly same way. So let's treat them exactly same way. So let's look how is a force multiplied by virtual displacement. And don't think, how is this virtual displacement, like how you can go and purchase it and what color is the virtual displacement. It is just a mathematical tool we need to make this mapping to be possible. Right, here. Okay, so you see that, okay, it's getting to be like a little bit of heavy. It's going to be heavier in a minute. But here is my virtual displacement relation that I learned in the case of external applied forces. I have here delta R and delta Q. A relation between the global and generalized coordinates is this numerical mapping matrix, partial R, partial Q. Okay, partial R, partial Q. That's how it goes. Now, let's substitute that information to my previous equation, and let's look how is that my generalized inertial forces can be written. So they can be written like this. And the guy that I'm particularly interested here is generalized inertial forces, that is this one here. And it can be expressed by using this monster here, where I have, let me explain what I have here. I have my numerical mapping matrix, and then my acceleration. And then I'm just taking this whole thing and I'm integrating that over the density of all the particles, and that's possible with this volume integral. That's how it goes. Oh, this is kind of hard. Okay, now the hardest part comes next. So this is still warming up. Why this is going to be more difficult? That's simply because this guy here will be very, very complicated. And it's going to be like this. Remember, second lecture, I think I did the second lecture, we express the acceleration using this equation. And then, excuse me, I'm a little bit disturbed that, I don't know if you hear this, but I hear that my family is making a little bit of noise. So maybe I should yell them something. Okay. If the voice is getting higher than this, I need to yell them a bit. Okay, so this is how I express acceleration. So I have here translational acceleration, and then I have this um, tangential acceleration, excuse me, this was a normal acceleration and tangential acceleration. So those were my three components needed in acceleration. And now what I will do, I will take this off. I will make a simple trick, and in my simple trick, I will reorganize my expression of acceleration such the way that generalized coordinates will be as an own vector. So here is generalized acceleration, here is generalized acceleration, and here is generalized velocity. So let me put these two guys, this one and this one, to same expression. And then let me take them, this and this as a one common component. So these two components can be written like it is shown here. So I have here identity matrix, meaning that is 2 by 2 matrix, where the diagonal components are equal to 1. Rest, there are just the two of diagonal components, those will be equal to 0. So it's going to look like this. Okay, then I have my rotation matrix that is differentiated with respect to angle theta, and then my vector u bar. And here is then my acceleration of generalized coordinates. And then I have here my second component, which is now a third component. And again, here I have two of these generalized coordinates, but the velocity level, not in an acceleration level. Okay, and I'm sure you know what's going to happen next. Next, we'll take this equation and I will substitute that to my previous equation, which is this one here. Okay, ready. So this is how it is. This is what I got from the previous slide. So this is simply my acceleration. This is my numerical mapping matrix. And I'm going to substitute all this information to this volume integral. This goes obviously here. This goes obviously here. So let's take a look. This, I know that this is like you're amazed, like, is this even real? Is this true? Yes, it is true. But there's going to be, after one more slide, things getting easier. So this is really the hardest point, definitely the hardest point. And I'm just doing this substitution, and this is how my generalized inertia forces are looking like. Now I need to do my mathematical operations. I just need to reorganize these components a little bit, such the way that I'm multiplying this one, and I'm multiplying that one, and I will get two components that are mass matrix multiplied by acceleration of generalized coordinates. Look, this is something that you are very much familiar with, so this is what I've been telling all the time. And then this is a quadratic velocity vector, and it's coming from the fact that this acceleration have component that is quadratically related to velocities. This is my component that is quadratically related to velocities. This is it. So now this is it. So now what we're gonna do next? We finally go back to real life. So after this involving mathematics, we're gonna take a look at this guy. What are the components that is consisting of? And then finally later we're gonna take what are the components that are making this quadratic velocity vector. This one here is called mass matrix, and this one here is again called quadratic velocity vector. Okay, mass matrix, that would be next. Are you still there? I need to take a look if you're still alive. Yeah, I see you following the streaming, but it's unclear if you're still alive. Okay, okay. Now that was the that nightmare that I said that we just have to go through this thing, and now things getting easier. Yeah, so brain death because of this. Okay, but let's forget about this involving mathematics, because I'm not going to ask that. I'm never going to ask like, okay, where, please divide me quadratic velocity vector starting from the Big Bang. I'm not going to ask that, but I ask what they are standing for. What are their physical interpretations? So with that, I'm going to take a look. How is that my mass matrix reads? And then I will have very, very interesting in-class quiz related to this. This is when you do all these mathematical operations, your mass matrix eventually look like this. Let's walk this through. So let's take a look. What are these components here? So my mass matrix consists of three different components. The one that is located here in the upper left corner is the diagonal matrix that is only including the mass of the body as the diagonal terms. Okay, this makes sense because think about how is an entire mass matrix. The entire mass matrix are related to generalized coordinates in such the way that the first one is Rx, second one is Ry, and this upper left corner is related to these translational coordinates. Well, translational coordinates only really what matters is the mass of the body, nothing else. Then I have here component that is located here in the lower right corner. That is a scalar component because vector multiplied by a vector will be a scalar, not the matrix, but the scalar component. This scalar component is a mass moment of inertia. So it's meaning like how much is the inertia resistant when you're rotating your body? Because again, remember this is related to angle theta, this one here. So it's angle theta, how much it is resisting the rotation. And that depends, of course, how is that you're rotating your system. Are you rotating this beam-like body, this bend from the one free end, or are you rotating that in the middle? So that could make a difference, like what is a mass moment of inertia? So we can take a look at that in a second. And then comes something a little bit of surprising. Then comes a component where translation and rotations are coupled. This is a component that do not have a clear name, but this particular component is equal to 0 if body reference coordinate system is located in the center of the mass. So if I have here potato-shaped body, here's a mass, center of the mass, and if the body reference coordinate system is located in the center of the mass, then this third component, which is located here and here, will be equal to 0. No name on it. So it's just a component that takes a place depending where the body reference coordinate system is located. This one here is a mass. This one here is a mass moment of inertia. This is exactly the same as the mass moment of inertia. You can take a look at the definition of mass moment of inertia, and you will learn that, okay, this is it. It's exactly that. Mass moment of inertia. And this third component is heavily related where the body reference coordinate system is located with respect to center of the mass. Mass of the body. Hear me now. Mass of the body is never ever changing. So if this Ben weighs, I don't know what it weighs, 10 grams. The weights, the mass is always same. It's not changing. Only what changes is how is the mass moment of inertia, because depending how I'm rotating my band, that is clearly different. You can even make this experiment in your home office by rotating the band here in the middle and in the one free end. So it's significant difference. Mass, this guy here, is never ever function of where the body reference coordinate system is located. Okay, so now we're going to take a look at the two examples, and then I will ask how much mass of the body will change as a function of the location of body reference coordinate system. Okay, so how much is that? No changes, because the mass is always a mass regardless how you measure it. Now, mass moment of inertia, that will change, of course, and then this third component, that will change as well. But let's take a look at these two examples, and then I'm ready to move on to in-class quizzes. So here I have a box-shaped body, and in my box-shaped body I have a length that is denoted as a L. I have H, which is dividing this direction, and the thickness here is considered as a W. Okay, and I would like to compute these three components of the mass matrix by using pure mathematics. Of course, in the real life, you should use a pre-calculate tables because those are the easiest way, but this time we want to make it in a hard way, meaning using just mathematics. Okay, this is a planar two-dimensional body, so I'm not going to integrate over this z direction here, but I'm going to just take this W here as a given value. So this is my integration here, and I might integrate this x-axis from here to here, and y-axis from here to here. Okay, so let's get started from the x-axis. So this is my equation again, and I'm going to differentiate that from here, which is a minus L divided by 2, to here, which is L divided by 2. So I'm integrating this area entirely. These are my boundaries. Minus L divided by 2 and L divided by 2. Oh my God, my handwriting is like no good. L divided by 2. You know that this is L divided by 2. How it goes. Well, I'm not going to show the details here, but what appears here is L. So I have now LW, and then I have this density here. Then I'm going to take my next direction, which is here to here, meaning from minus h divided by 2 to h divided by 2. What I'm going to get as a result, I'm using here symbolic math tool because I really have no idea about the mathematics. I'm just using the symbolic math tools. So I have here HLW, that's equal, then the volume. Volume multiplied by density is mass. oh my God, how it is so difficult. Volume multiplied by density is mass. Okay, that is then multiplied by 2 by 2 identity matrix. This is how the 2 by 2 identity matrix look like. And this is my first component that will be located in the left upper corner of my final mass matrix. Okay, two more components to go. Then this component here, which was previously called as a third component. I know that is not the good definition, but it's a third component. That will be equal to 0. I don't need to compute it, but if you would like to do this, you can do it that as an exercise, but really you don't need to do it because you can integrate this component here from here to here, and because it's looking at the balance, so it's like a linear equation, so there's going to be minus and pluses, so they will compensate each other, so it will automatically give you 0 as an answer. Okay, last one is my mass moment of inertia, and again I'm redoing the whole thing. This is when I'm using this integration of, this component, which is a vector u bar transpose multiplied by vector u bar. This is how you can write it. And now again, I will take the w as a given value, and I will do the integration from minus L divided by 2 to L divided by 2 in x direction, and in y direction, minus h divided by 2 to h divided by 2. Okay, x first. So then this is how it looked. I'm going to also look at the what is common here. Okay, I'm not. Yeah, okay, so this question was related to this one here, or the comment was related to this component. Okay, this component is just a mathematical thing that couples the translation and rotation if body reference coordinate system is not located in the center of the mass. But here it is located in the center of the mass. So it's not important. Okay, now finally when I do this y direction, this is what I'm going to get as a result. I'm going to use this definition, density multiplied by volume is equal to mass, and it's going to give me this equation. Okay. All right, I know that it's getting late, and it's almost time to wrap up today's lecture, but one more thing. This is finally how my mass matrix looks like for this particular case, where the body reference coordinate system is located here in the middle. So I have here a component that is this located here in upper left corner. That's 2 by 2 diagonal matrix. This guy here in transpose operation and without transpose operation is 0. And this is my mass moment of inertia. Now what I will do next is that I will redo the whole thing, but I will relocate my body reference coordinate system. And then there is a question like, okay, this is getting to be really, really involving. I know that this is hard today. In-class quiz will come in a second, so hold on, hang around, stay with me. It's going to be okay. It's going to be okay. I promise you that. Okay, now I have again this box-like body. I'm going to speed up a little bit too, because I don't want to look at too much about the basic mathematics. Now here in my case B, or whatever you want to call this, my body reference coordinate system is located in a one corner of the box-like body. So this is conceptually very different, because now the integration limits will be from 0 to L, from 0 to W. Oh, this, by the way, should be, of course, H. So I have a typing mistake here. So it should be H here. Sorry about that. I tried to remember to correct this before I'm putting this to model database. Okay, now again, W is given to us, and I can see that, okay, there is a comment. Okay, following, yes, understanding is difficult. Okay, let me just walk this through, and then we're gonna look this again, like pretty much what we did in the last week. Remember in the very end of the lecture that was pure pain. But today when we look at that again, it started to make at least a little bit of sense. So hopefully we'll do the same. Now, so I'm doing this integration first in x direction. So again, the integration limits are different. How much is going to make a difference in the case of mass? No difference. Absolutely no difference. Still, it's going to be L divided by H. Of course, this is a big mess. I'm, making mistakes about H and W here. Sorry about that. I need to correct it. But again, I have here volume multiplied by density. It's going to be my mass multiplied by identity matrix. So this is exactly the same that in the previous case. No difference whatsoever. The two components, the remaining components, they will be different. And they will be different because the integration limits are different. Again, I have this vector u bar x, vector u bar y, and I'm going to integrate those in those boundaries. 0 to L, 0 to H. Again, you just let the symbolic math tool to make it for you. When you do the x direction, this is what you're going to get as a result. When you're going to do the y direction, this is what you're going to get as a result. That then need to be multiplied by this guy, which is a rotation matrix differentiated with respect to angle theta. Eventually, you get these two components. You get the vector of two components. We'll show you how to do this by using symbolic math tool next week. And then the final thing is this mass moment of inertia, which you could get from the pre-calculated tables. But here today, we want to make an integration from 0 to L, 0 to H. And this is exactly the same equation than in the previous case, but because the integration limits are different, solution will be different. This time, mass moment of inertia will be mass divided by 3. And then I have here length power 2, h power 2. This in the previous case was mass divided by 12. So let me demonstrate it here. Where it is it? Here. Mass divided by 12, meaning that this value is lower value comparing the case when the body reference coordinate system is located in one end of the beam-like body or box-like body. And that's again this thing. So when you rotate it here, it's easy. When you rotate it here, not so easy anymore. So that's because the mass moment of inertia is higher here than it is here. Finally, we need to redo this next week, and we need to look a little bit about what this means us and how our life will be different when knowing this. But here's my summary. So here's my components. I'm going to place these to this 3x3 rotation matrix. Here is my diagonal part of the mass matrix. This is my mass moment of inertia. This is the component that do not have a name, but combines the translation and rotation. This one and this one change their value depending where the body reference coordinate system is located at. This one never change the value because it's a mass of the body. Okay. Then my class quiz is this. Okay, let me take this one, put this active on. Let me see how many people is following this. I have 91 students that are following this stream. Okay, there's a question if the mass matrix is the same which can be used in a model analysis. No, it's not. Model analysis is referring to something that there are flexibilities in a system. Here, we are assuming body to be rigid. So conceptually, very different story. Model, it is something that you use a finite element method or something to describe the structural strength. It's about the relation of mass and stiffness. Here we don't speak about the stiffness because we have rigid body. So it's kind of like meaning that stiffness is infinite. Okay, now I can see that the game is on. So there's a guess what is a success rate. And let me ask this question: how much the body mass will increase, decrease from case A to case B? This is my first case. Body reference coordinate system is located in the center of the mass. Case B, of course. is when the body reference coordinate system is located in a corner of the box-like body. Oh, this is okay. This kind of game is not acceptable. So saying that the success rate is less than 100, not not accepted. It needs to be exact 2 digits, 3 digits if it is 100%. Okay, but let me see. I have again 90 students. 65, 66 are already entered the answer, and the number is increasing. So the number is growing. So let's see how it's going to be today. 73. Okay, my personal, would you like to learn what is my guess here? I'm guessing, okay, I'm guessing quite low number. I'm guessing 65. Why 65? Because, remember where we get started. So we got started from very involving mathematics. So I'm sure that some of you were dead, mentally dead, once we were done with the mathematics. And then we came back to real life, but your brains are still in the mathematics. But this is what makes this course more challenging than many others. Because what I'm asking, it's just a common sense. It's engineering sense that you can simply solve this problem. But now you're thinking about this complicated mathematics and parcel this, parcel that, and you're not able to come back to this planet. So that's why I'm thinking that the 65% is a success rate in this in-class quiz. Hopefully it's higher than that, but we're gonna find that soon. Then there's gonna be another in-class quiz, and then we're done for today. Okay, 85 students. So in 5, well, there's a delay, so I don't need to do this. So I'm gonna just say that now enter your answer, because momentarily I will provide the success rate. So remember, 65 was my guess. 65. Oh, oh, look at this again. So look how close we've been in 100%. It's like ridiculously close. Do the math, but let's do the math. So we have here 86 answers. So it must be 2 incorrect answers. But without these 2 incorrect answers, you would get these extra points. But the rules are set. So what are you gonna do? Okay, so then I'm gonna take a look. I'm gonna show you the next in-class quiz. Now, while I'm introducing the next in-class quiz, I'm gonna read your comments. It's a little hard to read it, when I'm explaining or when I try to do this lecturing thing. So now I have a problem because the figure, this one is kind of in an incorrect location. So how can I make it in a better location? Well, let me try to relocate that a little bit. Okay. No, it's not willing to do it. I guess this is okay. Okay, so I have here a bit more challenging question. I have a box-like body. Body reference coordinate system is located in the center of the mass. And I'm asking, simply based on that information, what is a mass matrix for this system? And then I have the choices such the way that I have here, again, 3 by 3 matrix. And this term that is off diagonal term is non-zero. Then I have again 3 by 3 matrix such the way that is a diagonal representation. And then I have here 2 by 2 matrix, diagonal representation. And then my final one is a skew symmetric form of a mass matrix, as diagonal components are 0 and off diagonal components are mass. Okay, so it's still hard to see the question, so let me try to relocate it. So sorry about that. Let me make it smaller and now put more. Okay, is it okay? It should be okay. Okay, now there is a question about the in-class, not the class quizzes, but the weekly assignments. Weekly assignments, and there is a, if you miss the deadline, can you still submit it? Well, you can submit it if you make an agreement with me or Suraj. And there are some of you that had made a deal with me and Suraj. And the deal is very simple. So if you need to be someplace else, you have some urgent stuff to going on in your work, in your family life, you've been called to serve in army again, you let us know in advance and you say that, can I have a little bit of flexibility in terms of deadlines? Of course you can get a little bit of flexibility, but you have to let us know that in advance. So once we close the submission box, then it's simply closed and it is automatically closed and it's always closing at the midnight. So answering your question, you cannot submit it late if you don't have a permission to do so. Um, yes, there was a weekly assignment last week. I think, haven't I not updated the Moodle database? I'm a little bit surprised about that because I thought that I did that right after lecture. Maybe I was wrong about that. Okay, okay, but what about this in-class quiz? Let me take a look. How are the answers? Okay, I think that I have. Oh, yeah, sorry about that. My Socrates was not moved to next questions. My mistake. Okay, so you guys are saying that I did not update the Moodle last week. My mistake. My mistake because I thought that I have an assignment ready and everything. Okay, so I will keep you because of this mistake that I did. I'm gonna relocate the deadline such that you will have more time to submit your answers for last week's weekly homework. So we'll do that. So I don't know why that it's kind of like maybe too many things in my head. So I don't know why that because I should do it right after the lecture. Otherwise it will be simply gone from my mind. Okay, now Shockwave is on, so the game is on. So what about the success rate? Now it's get started from the super low values, 54, 99, maybe not that much. We'll see. By the way, because I never ever check my recordings other than cutting this part that is not important when I'm putting my streaming on. But I have a question to you because I can kind of hear that my family is making quite a bit of noise. So is this something that makes it hard to follow the lecture, or is it something that you don't really care about that? So almost there. So let me see, 72, 73 answers, 90 students there. So 15 are still thinking. So, okay, so you see that you don't hear anything. So that's good because I hear that it comes at least to, something that bothers me a little bit. Okay, but back to this game. So let's take a look. How is a success rate in today's in-class quiz? 90, what is it, 90 answers. So no background noise. That's good. So I'm thinking, okay, let me just show this to you one more time. Okay. And my guess for the success rate, again, I figured that this have to be 61, 61, 61. Okay, ready to see it? 69. Okay, all right, so not bad. So let's take a look. Let's go back to this one and then I will move on to teams. Okay, this option and this option makes no sense. And that makes no sense because the dimensions do not match. You know, I have to have a matrix that have a dimension 3 by 3. Otherwise, I do not have a component that match to my generalized coordinates, 3 generalized coordinates. Okay, so what is left is this option and this option. Okay, why is that the diagonal is correct? It is correct because look where the body reference coordinate system is located at. So it's the middle of this box-like body, middle. And because it's the middle, this off-diagonal components always will be automatically equal to 0. So that's why this option is correct. This could be kind of correct answer, but these guys are making it incorrect. All right. So with that, so it's 15 to 6. So we spent an hour and a half. So it's time to close this streaming. And still, again, I need to apologize that I did not update the model, but maybe we can make a deal that, so if you see that to happen again, please let me know. And you can actually, maybe you can be my model officer in this course. You can put that in your CV. So it would be model officer 2020 simulation of mechatronic machine course. And it model officer means that if something is incorrect in my model, let me know. With that, I'm gonna close this recording and I will see you momentarily in Teams. Okay, see you in a bit. Where is my, here is my OBS.